In this lecture, I want to go through some reactions of alkenes. And it's like, wait, weren't we just on alkynes? Yes, we're actually going to move back into alkenes for the next few lectures to finish out this module. And what I want to first start with is an important reaction that we unfortunately didn't get a chance to actually do in the lab, and that's the hydroboration oxidation of alkenes. Okay, in the hydroboration oxidation of alkenes, we actually do the exact same thing that we did for the hydroboration oxidation of alkynes. That is, we take our alkene and we put it through a two-step procedure. In the first step, we add BH3, and in the second step, we add NaOH and hydrogen peroxide. It doesn't matter what order I list the parts of step 2 in, the outcome is the same. We're going to get hydration of an alkene. Now, we don't form an enol in this case, so we're actually going to just stop with water being added. And I shouldn't draw the second hydrogen there. That's not helpful. But it's a net hydration of an alkene that does not follow the Markovnikov rule. So we call this, I suppose, an anti-Markovnikov hydration of alkenes. So it's an anti-Markovnikov hydration of alkenes. So again, kind of a bummer we couldn't do this one in lab. There's just only so much that you can do in a semester in the midst of social distancing and COVID, but the reaction is the same kind of two-step procedure and really follows the same mechanistic stuff. That is, we should know the step 1 mechanism. And in step 1, we add BH3 to the alkene, where BH2 goes to the less substituted carbon, and H goes to the more substituted carbon. Okay. Now, additionally, the BH2 and the H are added syn to each other, and we'll see why that's important in just a second. So they're added syn to each other, or the same face of the alkene. Okay, so let's go ahead and consider how I would actually solve this problem. Like, well, in lab, we would take this is 1-octene, and we would add BH3. Well, let's do the arrow steps like we usually do. So step 1 is BH3. Step 2 is NaOH and H2O2. Okay. So we have those two things added together. That's going to get a product where we've got H and OH added, such that the OH is at the more substituted position, or excuse me, less substituted position. OH is at the less substituted position. Hydrogen is at the more substituted position. Now, the mechanism for this involves really just showing that you can form the first intermediate where H and BH2, just take two curly arrows, simultaneous addition of both hydrogen and boron in one concerted step. put boron and hydrogen together. This intermediate is then oxidized in the sodium hydroxide H2O2 step. So we've solved the product, we've shown the mechanism for the first step. Basically just providing the structure of the intermediate is what I care most about, and then understanding there is some syn addition. Now the syn addition is important in ring structures. So can I explain the outcome I'm about to show? What if we take methyl cyclohexene and we add to it, well, sorry, not add, let's just draw the arrow as we typically do. Step 1 is BH3. Step 2 is NaOH and H2O2 being added for the oxidation sequence. The outcome of this reaction is, I'll give us a second if you want to pause the video, spoiler alert, that sort of thing. Okay, we would get both enantiomers where the hydrogen and the OH are cis to each other and the methyl group is trans. So this is plus the enantiomer where you flip everything. Just as long as the OH and the H are cis to each other, and the overall structure in this case only has two substituents, a methyl group and an oxygen, which are opposite to each other. So we call this overall trans. But the hydrogen and the OH, the things that were added, are cis to each other. Okay, so why is this the case? Well, if we consider the mechanism, we actually get syn addition of B and H. So the intermediate arising from B adding here and H adding here gives us either both wedges or both dashes for the H and the B. We haven't done the oxidation step yet, so BH2. Okay, I want us to note that we've got two carbon atoms on our alkene. The red is less substituted and the green is more substituted. The red carbon has two groups attached to it. Okay, the carbon, it's got a hydrogen and then another group for the at the alkene carbon. Whereas the other carbon, the green carbon, has three groups attached to it in total, the alkene carbon-carbon double bond, in addition to two other non-hydrogen substituents, rest of the ring, and then a methyl group. Less substituted, more substituted. And as a result, we get syn addition with the boron selectively going at the less substituted position, that carbon that's outlined in, highlighted in red, and the hydrogen goes to the carbon outlined in green. And when we do the oxidation, it turns out, interestingly, the oxidation goes with retention of configuration. Whoops. Retention of configuration. So whatever the boron was, that's what the oxygen becomes when the oxygen replaces the boron. And I show specifically the formation of one enantiomer, but both enantiomers are formed. You could have the BH2 adding syn from the top, bottom, or syn from the top to give rise to both enantiomers, but you don't see a mixture of diastereomers where the methyl group and the OH are on the same side, because that would be the wrong mechanism for this. So it's anti-Markovnikov hydration with some stereoselectivity and high regio selectivity for the, I guess it's high stereoselectivity. Yeah. Okay. Anyway, so that'll do it for the hydroboration oxidation of alkenes, or the anti-Markovnikov hydration of an alkene. So next time we'll look at more anti-Markovnikov reactions involving free radicals at this time.